Genau, Frau McClelland kommt vom Julius-Kühn-Institut. Sie hat einen sehr technischen Hintergrund, eigentlich sehr informatiklastig, ist eigentlich ausgebildete Softwareingenieurin mit Schwerpunkt Luft- und Raumfahrtsoftwareentwicklung. Sie haben selber auch schon eine Firma mitbegründet in diesem Kontext, Brand Perspective GmbH als Senior Softwareingenieur, und sind dort verantwortlich gewesen oder immer noch für den Aufbau der initialen Softwareentwicklungsinfrastruktur. Jetzt haben Sie Ihr Spektrum nochmal erweitert um den Bereich Geodaten und arbeiten jetzt als Geodata Scientist eben beim Julius-Kühn-Institut mit Schwerpunkt in KI und Standardcoding für die Umweltforschung. Da geht es viel um Cloud Computing, Übergang zu großskaligen geodifferenzierten Cloud Computing für die Verarbeitung von Satelliten, Standardcodungsdaten mit Python und darüber hinaus noch um die Themen eben Datenintegration, ich glaube, das ist da schon angeklungen, und die Entwicklung von automatisierten Pipelines, um Analysen zu automatisieren. Genau, Sie haben einen Vortrag eingereicht mit einem langen Titel, Building a Reusable Infrastructure for AI Applications in Agriculture, Tackling Data Fusion, Privacy and Interdisciplinary Challenges with Multi-Source Earth Observation. Ich glaube, das geht in Deutsch.
Das wird in Englisch sein.
Alles klar, kein Problem.
Ja, hallo zusammen. Ich hoffe, das ist in Ordnung, wenn ich auf Englisch den Vortrag halte. Ich bin das so gewohnt und möchte meistens sicher gehen, dass alle auch verstehen. So again in English now. The topic I will be talking about is about building a reusable infrastructure for AI applications in agriculture. And focusing on the areas of tackling data fusion, privacy, and interdisciplinary challenges with multi-source Earth observation data. So, as already mentioned, I am currently at the GEO.KI. So, for those who don't know this is the Federal Research Institute for Cultivated Plants, and there is a department responsible for strategies and impact assessment. So the research put into this topic I'm going to present started out in the NALAMKI project. This stands for Nachhaltige Landwirtschaft mittels KI. It was then applied for a use case in the ENTO-PROG project in tight cooperation with the ZEP Institute, and is now ongoing work within the Monvia project. So the Monvia project, just to get it right, supports nationwide agriculture monitoring of biodiversity. So although we know that the potential of artificial intelligence in agriculture for using remote sensing data is very promising, the potential is very promising with remote sensing data for environmental protection in areas like, for example, yield prediction and harvest optimization, soil erosion detection and prevention, or BBCH stage recognition for precision agriculture. This leads to the assumption that many similar technical issues have to be tackled within all these different areas when it comes to preparing the data and the infrastructure and pipelining for artificial intelligence. So now we focus on a specific use case of plant growth phase recognition, for example, with BBCH phases with remote sensing data. Here again, there's a lot of potential for sustainable agriculture, for example, water conservation, sustainable land use, or, as in the GEO.KI project, pest and disease prediction. When looking at this topic and applying remote sensing data for artificial intelligence, specifically for plant observation and preservation, we have a very broad scope. So when designing this architecture, we focused mainly on building on European open source solutions, applying federal research accessible tools, using as many open access databases as possible that cover Germany, and then, of course, towards the use case and the availability of the reference data that we have available. At the end, the main goal was to be scalable, transferable, and extendable. So the state-of-the-art open source solution from Europe by 2021 is through the Copernicus program, since some of you might know. We access this data via the CODID virtual machines and use the ESA-provided SNAP tool. At the GEO.KI, it is already employed the Rasterman GEO Raster Data Manager for data cubes of diverse types that we use to store the data. It has a OGC WCS interface to the outside, and we also have a web interface where different services and process data cubes can be presented to the public, called the GEO.KI web application. So in looking at the selected data we were working on, they all have their specific characteristics that lead to different challenges. Both of them have quite long pre-processing chains, all the way to CODID, which has a high potential for errors and gaps. Then the Sentinel-2 optical data has additional potential for gap because of cloud coverage that's also quite known. And the SAR data has even more longer and complex processing change, which leads to even more gaps in the data sets. We also decided to use the DVD weather data and year data. More significant are the challenges with the reference data, which has already been mentioned, specifically for plant growth phase observations. So the thing about this data is it's often manual labored by farmers and agronomists, which lead to other sources of errors, and it's difficult to work with. Then there's the very important topic of data privacy and data ownership. And at the end, all the different data comes in different formats and coverage. But as we know, this is the most relevant for successful machine learning and AI. So at the end, when we put this all together, this is how the fusion data looks like. So it is homogeneously incomplete over time, whereas the time aspect is quite relevant for plant growth phase observations. So this is the general approach of the infrastructure. So it's all based on a central PostgreSQL table structure, indexed with field IDs and timestamps, where all the data is prepared and entered in, but only specifically for days where there is reference data available. After all the data is entered in the database, this can serve as a black box, where the origin or the location of the data is then concealed and no longer trackable. The database itself provides a unified access, and after looking at the coverage of the individual data types, a suitable machine learning method can be selected and applied. So these are the typical pre-processing tasks towards machine learning analysis. For each of these tasks, we tried to develop open source solutions or open access databases to provide to other scientific projects. So for one, we developed a Sentinel-1 batch pre-processing tool where certain vegetation analysis parameters are pre-processed according to field and time range, and give out time series for specific analysis. Then, with this tool and with another pre-processing chain for Sentinel-2 data from earlier projects, we processed Germany-wide coverage of optical and specific parameters from SAR data for the years 2017 to 2023. And this is also accessible open access via MapViewer. Then it was also helpful to develop a time series generator tool for further relevant parameters for the analysis, but based then on the reference data. So the fields where there's reference data and the time ranges or days are given into the tool, and then it gives time series of this. So this is now the data flow diagram of the infrastructure, showing how everything plays together. So the Sentinel-1 preprocessing tool preprocessed the data, put it into Rasterman as a data cube of Germany of Sentinel-1, Sentinel-2 data. Then the time series generator can derive the time series for the specific reference data and enters it directly into the PostgreSQL database. From then it can be observed from the machine learning module, where a specific machine learning model is selected for the coverage, and the training validation test data sets created, and the models evaluated. So in the scope of the GEO.KI project, we analyzed and compared 4 different machine learning algorithms. The first one is the classical generalized linear modeling. Then 2 tree algorithms, random forest and XGBoost, that are also very widely common for classification. And then we used multi-layer perceptrons for also classification, quite simple deep learning methods. So here's the visualization of a subset of the reference data analyzed of 17 fields. So the radar data covers 144 observations of all the available fields. So 0 to 19 is not correct here, so it's all the available fields covered by the SAR data. In comparison to that, we see on the left side that the Sentinel-2 data does not cover even half as many of these points. On the bottom, we see the scattering also of the fields over time. And obviously on the left side, it's not that much. So here is a comparison of the feature importance of different combinations, where there is the condition that for each of the selected and analyzed 0 to 19 phases, there has to be at least 3 observations. So this results in 5,400 different satellite image pixel. The optical data did not fulfill this requirement, so we continued to analyze only the SAR data. So we see here that the radar vegetation index from the radar backscatter and the coherence have different feature importances. The coherence is higher, and although they both are quite low, they add to, they're very significant in the model performance. So these are some concrete results of this very small selected data set. As an example, we at the end actually had 228 fields and 2,506 data points, reference data points that can be processed and analyzed with this infrastructure. So random forest performed quite well with 93% on these phases. XGBoost easily outperformed it. MLPs, whereas it was important to not cause overfitting on this relatively small data set, have an accuracy of 71%. And as we see on the left, GLMs cannot model plant growth phases as expected. So the outlook with the infrastructure is now to migrate from the CODA-DE virtual machines to high processing clusters provided, or one cluster provided by the KIDA, so that more high resolution satellite imagery can be analyzed and more complex processing. Then we would like to integrate digital twin LIDAR fusion data, which can also integrate well into other web service that a colleague developed in another project in the past. And then try to transfer the infrastructure to a new use case of towering vegetation recognition within the Monvia project. So to sum up our main insights, Repetitive tasks can be reduced with open source and reusable solutions. Reference data acquirement is still a very relevant and ongoing open topic, especially in plant growth stage analysis. And sometimes it's best to keep it simple, because in some cases, conventional machine learning methods are sufficient and it's not necessary to apply deep learning methods. So if anyone's interested, these are the links to all the open source and open access solutions developed in this scope. And yeah, there are some publications with further details on the concrete pre-processing chains in the abstract that will be provided. So thank you for your attention. Fragen können auch auf Deutsch gestellt werden.